Latin squares in statistics applications are grid designs with predetermined layout rules for their rows, columns, and treatments that are useful and efficient for three-factor ANOVA analysis. Looking at a short history of ANOVA analysis, we see that if I and j are two variables in an experiment, we would need I times j amount of treatments to have a complete layout design where every possible combination of variables in an experiment is tested. Although a complete layout provides very comprehensive and reliable data, we must move past two-factor ANOVA to include more variables. It becomes difficult and very costly to use a complete layout design, so we need a smart and efficient incomplete layout design that will give us a diverse cross-section of the data that represents many different areas of the data range. Latin squares are one of our best options because of their straightforward and predictable rule structure. In Latin square designs, it is assumed that all lesser than I or j factor combinations are absent, so a 4x4 Latin square would only deal with 4x4x4 rows, columns, and treatments. So each row, column, and treatment is exactly represented 4 times. The defining characteristic of a Latin square and what makes them so efficient and diversely representative is the fact that each treatment, the letters A through D, appear exactly once in each row and each column. In an engineering application, such as finding the most efficient computer hardware setup to run 3D CAD modeling, we could use a Latin square design to analyze 3 factors in our machine. We could assign the type of processor to the rows, the type of graphics card to the columns, and the modeling software suite to the treatments, and have a diverse but efficient set of 16 outcome data points that each take all 3 factors into account. The Latin square output data can further be analyzed in basic 3-factor ANOVA Excel techniques and appear and behave similarly to what we are used to analyzing in 2-factor ANOVA. Although the Latin square still provides for an incomplete layout, it represents a good cross-section of the data for accurate and reliable analysis in situations where efficiency in data collection and analysis is key, making it a very good option for 3-factor ANOVA design.